Okay, so it's a pleasure to have our own Wout Merbis telling us about his work on exact epidemic models and tensor product formulation. Go ahead.
Right, thanks very much. Thanks for joining today. So I'm a theoretical physicist. My background is mainly high energy physics. Now I'm interested in looking at stochastic models, trying to find ways to use tools and techniques from many-body quantum systems and apply them to stochastic systems. I'm very happy to do this at DIEP, where many people from different backgrounds come together to study emergence, and this needs a sort of interdisciplinary approach because emergence properties occur at all length scales in physics. So this is my emergence intro. Sort of if we divide physics or physics nature in different length scales, then we can find emergent properties everywhere, and typically they involve some microscopic system with sort of simple rules that may or may not be known to us, and then taking a big collection of those microscopic systems together creates some sort of macroscopic properties that are hard to explain from the individual constituents, but sort of arise as a result of the collective behavior of them. And so on the small length scales, we know we have the rules of quantum mechanics that govern how fundamental particles interact. And then if you take a lot of them together under the correct circumstances, this could give rise to sort of superconductivity or Bose-Einstein condensates or exotic phases of matter that are really a result of the collective quantum behavior of these, having many of these constituents. But of course, fundamental particles can also form atoms and molecules that can be very complex, that carry information on how to construct cells, which themselves sort of interact to form living, breathing organisms like bunnies, or create neural networks in the brain that lie at the basis of the emergence of intelligence and consciousness. And those sort of intelligent and conscious beings can then interact in society with each other to create collaborative efforts or risk the chance of creating a pandemic like we see this day. And all these sort of chains of interdependencies, often they are cut to study the systems more detail as a sort of stochastic system. So we don't really have to take into account all the details, but at some sort of level of approximation that we'll make, we'll just suppose that the microscopic system is a stochastic system of random interacting random variables, let's say. And this is well exemplified in this epidemic example. We don't really care about each individual's mental state, for instance. We just care whether they are infected with some disease or whether they are susceptible to it. And then you get sort of transition rules based on Markov chains that can describe for you how the infection will spread through the entire population. And in the last 20 years or so, really an explosion in work has been done since the discovery that complex interaction networks sort of underlie many of these emergent phenomena, and that they can be modeled using the stochastic systems. And mainly this progress has been sort of experimental, trying to uncover these hidden network structures, but also numerical, and try to simulate, say, how these network structures influence epidemic spreading, for instance, or the other emergent properties. And maybe sort of the really solid theoretical foundation maybe lacking a little bit behind, especially if you look sort of in this tier, right? We know as human beings now to create algorithms that can outperform human beings in certain tasks, but nobody really knows why it all works so well. And in the epidemic spreading example also, it's not so hard to find some papers in which they say, well, analytically, not much is known about this, so we resort to numerics. And so my entry point is sort of to look at the similarities between making this transition up here, of which there is a lot of very beautiful mathematics that is sort of being developed to go from the individual quantum particles to the composite system, and to see what kind of lessons that have been learned here can we apply to this epidemic spreading example. Okay, so then you could say, well, you're crazy, human beings are not quantum mechanical, so what do you really mean? Apply lessons from quantum mechanics to stochastic systems. And since this was a discussion that has been raised before in these journal clubs, I thought it would be nice to just make a list and play this game, quantum versus stochastic. And so my entry point will be to go from quantum to stochastic. Usually people make this list the other way around, right? You say classical probability you have here, and then you do quantum, it's going to be different. But I really want to sort of translate an operator formulation from quantum mechanics into an operator formulation for stochastic mechanics. And so this list has been sort of inspired also by this work by Baez and Piemonte that Mauricio mentioned in the Slack channel. So some credit goes to them as well. All right, so in quantum mechanics, we know the constituent particles of these sort of individual particles can be described by wave functions. These are complex vectors that live in a Hilbert space. I'll be restricting attention mostly to finite dimensional Hilbert spaces or finite dimensional vector spaces. And these complex wave functions, they are normalized such that if you take the inner product of the complex wave functions with its complex conjugates, then you get one. So this is sort of called the L2 norm. If we go to stochastic systems, we are dealing with discrete probability distributions. And so also in a finite dimensional case, I can organize that as a vector. I just say all the elements of this vector are the elements of my probability distribution. And then the normalization is that sort of the vector should sum to 1, which I'll denote with this contraction with the co-vector. So this guy means it's a row vector and all the elements of this row vector are 1. And so then if you contract that with the column vector, you get the sum over all probabilities, and that has to be 1. All right, so that's sort of mimicking this step. Then we go to expectation values of observables. So in quantum mechanics, observables correspond to operators which act on these wave functions, and to compute their expectation value, you have to sort of sandwich the operator, which is just a matrix, with the wave function and its complex conjugate. And so this is sort of the operator statement of Born's rule that says that the probability of finding your system in the state A is given by the square of the components of this wave function. In the stochastic case, we can do something similar. Of course, we know that the probability of finding a system in state A is just the 8th component of this vector. And then we define a projection operator that reads out the 8th component in a sort of similar way. So if you act, this will just be a simple matrix that gives the 8th component of this vector, and then taking this norm, which is called the L1 norm, simply returns the 8th component. So it might seem like a roundabout way of reading out the components of this vector, but it will be useful later on to know that we can always use these projection operators to read out individual components. Then we have time evolution. In the quantum mechanical case, this is of course Schrödinger equation. And so the system evolves in time by multiplying it with some matrix that's called the Hamiltonian. That has to be a Hermitian matrix, namely its complex conjugate transpose has to equal itself. And the only reason why it has to be this Hermitian matrix is because this constraint up here has to be conserved at all times. So at all times, we want the sum of all probabilities to be 1, right? But in the stochastic case, the constraint is different. And so if we do time evolution, also the matrix that appears here, that's called Q, the infinitesimal generator, it should satisfy a different constraint, right? So this equation is called the master equation. Q is the transition rate matrix for the infinitesimal generator. And in order for the total probability to be conserved under time evolution, we want this guy to have columns which sum to 0. So that's denoted by this constraint. Of course, if I contract from the left, I get a row vector with all ones. I contract this with this matrix that gives you the sum of all the columns. And I'm saying that that should be a row vector with all zeros. So each column has to sum to 0 individually. So that's a very important property. And so then...
there's a question from Michael on the chat. Can you read the chat? Or?
Oh, I'll open the chat. I hadn't opened the chat. All right. There's no need to restrict to projections in the stochastic case. Yeah, so in principle, operators can be real matrices. So you don't have to project to a specific component. I don't know if that's going to be the question, but in practice, I will work in a basis where you always just project to a specific component.
What can I ask another question?
Yeah.
So I mean, in the quantum case, you're working with Hilbert spaces in L2, and then I mean, you can define an orthonormal basis of functions, and then the inner product and the Hilbert space, and so on. In a stochastic, this structure is somewhat lost. So
I'm going to say that these vectors are so that's something I should have mentioned. So I'm going to say these vectors, they are real non-negative vectors that are normalized in the L1 norm. And so they live in a vector space of real non-negative L1 normalized vectors. So this is sometimes called the L1 space. I'll just refer to it as a probability vector space, denoted by this P. D denotes the dimensions of this vector. So you still can have orthonormal bases of this vector space. And inner products, well, in this case, the norm is just you have to you have to replace everywhere the norm with the L1 norm.
Yeah, I think it's more like that L1 gets paired with L infinity, right? Like the observables are more like bounded functions. So the orthonormality is maybe a bit strange, but I think the tensor product is still fine. But you can still, a composite system is still given by tensor product of the function.
That's going to be the next. That's going to be the next point, indeed. So thanks for that. So that's so the composite system described by the tensor product of the individual constituent Hilbert spaces in the quantum mechanical case, but that's just a sort of linear algebra kind of statement. That means we're keeping track of all possible combinations. And so we can copy that to the stochastic case as well. So describing the composite system is just a tensor product of these component probability vector spaces. Okay, so at this point, I have to sort of step back a little bit and say, what is the tensor product? Because if you don't know, the rest of the talk will be sort of useless. So instead of letting you go to Wikipedia on a different tab, I'll just write here what's written on Wikipedia. So the tensor product of two vector spaces is a vector space itself that has a bilinear map from the Cartesian product, which is like the outer product, to this tensor product state. So if that was not very useful, maybe the sort of a practical definition is just to think of it as taking Kronecker products. So if you have two matrices and you tensor them together, that's going to give you a bigger matrix where all the elements are all possible combinations of products of these smaller matrices. And so this is just a way of keeping track of all possible combinations of these matrices. And of course, if you then again tensor this guy with another 2x2 matrix, is going to give an 8x8 matrix. And so the dimensionality of this thing is going to grow exponentially with the number of tensor products that you add. But that's not the only sort of property that tensor products have. The most useful thing that actually maybe the only thing that you should remember that tensor products have maybe is this property. So if you have two matrices, they are both constructed from tensor products, and you matrix multiply them together, that's just denoted by this dot, then you can compute the same thing by first matrix multiplying the constituent matrices, provided that, of course, the dimensionalities match up correctly, and then taking the tensor product. And so that means that if you want to compute a series of products of matrices that are all tensor products themselves, you don't actually have to compute the explicit tensor product. You can apply these matrix multiplications locally within the tensor product, right? And that gives you the possibility to define local interactions or local transition rate matrices. And so these infinitesimal generators Q, we'll take them to be bilocal if they can be written as a product of two non-trivial operators that are both tensor products, but they're very simple tensor products because they're tensor products with all identity matrices and only one sort of non-trivial operator inserted at side I. So this guy is a local term. This guy only has this non-trivial operator inside I, and all the other n-1 sides are just identity matrices. They act trivially and they don't do anything to the states. And so then when you have this bilocal term, you can view that as n-2 identity matrices. And then at side I, we act with operator O1, which does the matrix multiplication. And at side J, we act with an operator O2. So then if this whole thing acts on a big vector that is a great big vector in a big tensor product space, then each term only gives a local operation or a bilocal operation on two sides, while all the other sides are unaffected. And that's because of these properties, you know, all the identity matrices, they will just go through to the sides and they'll just do nothing. And only the O1 and O2 will act at side I and J. So let's see how that works in the binary system for Markov chains for stochastic systems on networks. So we're going to say we have some network of nodes connected by edges that are taken from an adjacency matrix denoted by Aij. And to each of these nodes, we will assign a probability vector. In this case, it takes values in two deterministic states, so two basis states. We have S and I, just for the epidemiological example that I'll discuss later. So S would be susceptible, I would be infected. And then each of these vectors is a probability distribution whose components are the probability that this node is susceptible, the probability that that node is infected. So they are not independent, they have to sum to one, but it's still useful to use a two-dimensional representation. Because by using these 2D vectors, we can act with transition rate matrices that are 2x2 matrices on them. We already discussed that they have to be infinitesimally stochastic, which means their columns should sum to 0. And so in 2Ds, there are only really two independent, linearly independent matrices which have that property. Either the columns are 0 or they are -1 + 1. And so the -1 is always on the diagonal. And the reason for that is that in that way, none of the individual components of this guy will become negative. So that's another requirement. And then, so using...
sorry, well, can I ask a question?
Yeah.
You have here this normalization constraint. Is this normalization done per node or for the whole network?
So each node is normalized like this. Yeah.
Each node, okay.
Yeah, that's yeah. But also the whole network. Of course.
So this just it would be just like a marginal probability then this in the nodes that this. So it's condition that you are on that node, either you are susceptible and infected. Yeah, okay.
So this it's just saying that the node has probability 1 of existing and probability rho s that's susceptible, rho I that is infected. Yeah, and that holds for each node.
Okay. Thanks.
Yeah. So then we take the composite state, so the state of the whole network. We take this to be this tensor product or a vector in the tensor product space where we have n of these individual two-dimensional probability vector spaces. And that vector is called separable if you can write it as a direct product of the individual nodes. So the individual probability vectors, if you take a direct product of them, and then the state is separable, that's not the most complex state that you can have, of course, because this means you only have to specify n vectors to get the complete state. And so the most generic state is not separable, but it's a linear combination of all the possible microscopic configurations that this network can have, right? So if I1, I2, etc. Labels the basis states, S and I, then there are n nodes that can take 2 values. So there's 2 to the n possible microscopic configurations, and the generic, the generic state is just a big tensor that can have 2 to the n components. So this is sort of the most complex thing. This is the least complex thing that you can write. And then these transition rate matrices, Q for the composite system are by local operators only involving these nearest neighbors in the network. So whenever we have a non-zero entry to Aij, we add one of these bilinear terms. So they operate only at I and j locally, and they don't do anything in the rest. And then you sum over all edges. So for each edge, you add one of those terms. And you can add a local term as well. So that just means sort of an inherent transition that does not depend on the state of the neighbors in the network. And now the question is which operators to put there? Well, that will depend entirely on the system that you're interested in. So the stochastic rules of the microscopic constituents of your model. And so then we go to the example where we impose these rules. Okay, so the SI model in epidemiology is the most simple thing that you can possibly write down. It only has one transition, and the rule is that an infected and a susceptible meet, and then with some probability tau, the susceptible could become infected. So to find this transition rate matrix, we take for each edge in the network. So whenever this transition happens, you can say that these 2 nodes are connected by an edge in a network. And then so for each pair sharing this edge, you have to perform the following operations. Well, at the one side, we have to check whether they are infected. So that's done by this projection matrix. And if you act on the individual nodes, let's say you see it returns the probability that this guy is infected times the infected basis state. And at the other end of the edge, so at node J, we have to check whether they are susceptible. And if they are, we have to flip it to infected with some probability tau. And so the matrix that does this flipping is this QS2I matrix, and it removes susceptible probability and it adds infected probability, but it only does so if the node is susceptible. That's why it's in the first column. So if you act on a node, you get the probability that this node is susceptible times now a vector that is called an infinitesimal stochastic state, which has the property that the columns sum to 0, right? And that's nice because you can add this state to a stochastic state, which has column sum to 1, and you don't ruin this column sum. And so I can add this to, for instance, this one, and then, well, not this one, you got negative things, but you can add this to, let's say, the susceptible basis state, and then you'll see, okay, that takes away susceptible and adds infected, so it flips it to infected. So eventually, so you put it together, so you have these two operators that give you an infinitesimal stochastic matrix. And really, basically, all this does is providing a matrix formulation of what you would write down in your computer code if you are programming this on a network. If you would program this dynamical system, you would say something like for all edges in the network. So that's this sum. Check if the one end is infected. Check if the other end is susceptible. And that's because it's in the first row. And then if it is, subtract susceptible probability and add infected probability with probability tau. So this is sort of the matrix formulation of writing that for loop in your code. Then if we wanted to deal with more complex models, we can add recovery and we get to the SIS model. So besides this transmission of the infection, it allows for infected individuals to recover with a rate gamma. But if they recover, they don't get any immunity. They just go back to being susceptible. So we can stick with the two-state model, but still have another transition. So then that sort of adds an extra term that we have to add. So we have to check if the node is infected and flip it to susceptible with probability gamma. So this is done by this other transition rate matrix, QS2I, which also produces this infinitesimal stochastic state, but this one sort of removes infected and adds susceptible again. So the full thing is given by the same term that we had, plus for each node, we add this, we add this QSI2S term tensored with n-1 identity operators, just that each term only acts locally on any individual node. Okay, so could go on and generalize to multiple compartments where you have more possible states like recovered or exposed, more transitions, and so the paper has sort of a general rule to translate compartmental models that epidemiologists like to look at into sort of transition rate matrices for that model on a network. We could talk more about this afterwards, but I wanted to spend the rest of the talk on some other things, some other aspects. One thing is, of course, that these transition rate matrices with the bilocal interactions, they correlate the nearest neighbors in the network. And you can see that by sort of computing the time-dependent state. You have to find this matrix exponent. In simple cases, you can just do it. But the point is just that even if you start with a separable state or independent random variables, then after time evolution, this thing cannot be written as a separable state. And so it's correlated in that sense. And if you do restrict to separable states, and then write down the rate equation or the master equation just for the separable states, then what you get is individual-based mean field theory approximations that have been studied a lot in the literature. So, for instance, this paper by Van Michem and his group. And so these sort of individual-based mean field theory approximations give the evolution of the probability that the node I is infected, and it has then a nonlinear term because it depends on the probability that the neighbors is infected. But sort of the assumption in deriving this formula is that the neighbors are actually statistically independent random variables. Okay, so I could also show you the derivation in more detail afterwards, but to do something else, to do anything useful with knowing that these transition rate matrices are now sort of local operations, we still have to compute these matrix exponentials, right? So it can be very hard because the Q in principle exponentially large matrix. And so here what we'll just do is the most basic thing that you can imagine doing is taking this S to I transition that was sort of the simplest epidemic model that you could think of, and expand it in time just by expanding this matrix exponent for some simple initial conditions. So in this case, sort of the initial conditions are that the entire population is susceptible, except that at time t equals 0, we flip one person to infected, and then we follow the spread of the infection through the network, and that's done by acting repeatedly with this transition rate matrix on these simple initial conditions, and then it becomes useful to have this bilocal property. Okay, so I wanted to show in detail how that works. So it's nice to show this with a graphical notation. So I'm gonna suppress all the susceptibles because they don't really do anything if they're not close to an infected. And the infected I will denote by a white circle. And then there's this other player that was quite important, which was this infinitesimal stochastic state, which I'll denote by blue nodes. So these guys, if you sum over them in the L1 norm, for instance, it will contribute 0 because the columns sum to 0. So that's important to remember. Then, because this transition rate matrix was constructed out of local operators, we have to know what these local operators do on these states. So the projection on the susceptible just gives 0. The projection on an infected is trivial operation, right? So an infected is just gives infected. But if you project on one of these blue nodes, then you're going to set to 0 the top component, and then you end up with a white node. So P on a blue node turns into a white node. Then you have this QS to I transition. If that acts on one of the susceptibles, that creates a blue node. If it acts on an infected, it gives 0. You can't reinfect the infected. And then there's this sort of interesting relation that if it acts on a blue node itself, it gives a minus sign. And that's actually quite nice because, you can imagine that if you do this over and over, you'll get repeated signs in the expansion. And that's nice if you want to resum things, because then it would sum to something like e to the minus t, and eventually, your series will converge. And so that's all thanks to this minus sign. Okay, so let's see how that works in practice. Of course, QS to I also introduces an edge from the network. And so at linear order, we only have, first we have patient 0, and then we act once with Q S to I. The only thing we can do is really project on patient 0 with P, and then with Q we can act on a new node. And so that gives you the contribution at linear order. These are all the neighbors of patient 0 that are now blue nodes that are being infected, right? But so to use this diagrammatic notation to actually compute some things with formulas, you know, we have to compute expectation values. And as I mentioned all the way back in the beginning, to do that actually is another operation of this projection operator on this state, right? And so what that does is it makes sure, so we have to do another projection operator and then take the L1 norm by summing over all the elements, right? So in taking this L1 norm, you immediately realize that whenever you take an L1 norm on a blue node, that whole term is going to give 0, because it will be something multiplied by the sum of these elements, which is 0. And so the only sort of non-trivial contributions are going to be diagrams without blue nodes. And so the only non-trivial contribution is when this PI acts on the blue node and turns it into a white node, right? And then you'll get a non-trivial contribution from all the edges that you have here. So the message here is that if you want to compute single node expectation values, it suffices for you to know single blue node diagrams. Okay, and so this is just a linear term. If we want to, but you all know, you know, these epidemic models, they have exponential growth. So this linear approximation is going to be valid only for a very short time, and we have to, you know, figure out what are the dots here. So fortunately, we can think of this transition rate matrix as sort of as a subgraph constructing algorithm. So there's some systematics into which kind of subgraphs will appear in this expansion. So the first rule is that, well, Q could act on a new node, P could act on any of the white nodes in an existing diagram. So then at the next order, you'll have a diagram where there's a new blue node attached to each of the white nodes in the existing diagrams. So that's the first rule. The second rule is if Q acts on a new node and a new susceptible, and P acts on a blue node, then what happens is that blue node turns white and the new blue node is attached to it. So that's sort of following the infection spreading along a chain. This is sort of branching out from each of the infected. And then there are some less obvious rules. We could, for instance, have that Q acts on a blue node and P acts on a white node that already exists within the diagram. Then an additional edge between those nodes is added. And because Q acts on the blue node gave a minus sign, so we have to drag this minus sign. So when I write a 2 above an edge, that means that the adjacency matrix entry for this edge appears squared in that diagram. So in principle, later on, I will just take all of the adjacency matrix elements that are not 0, I'll take them to be 1, and then we can forget about these 2. But in principle, if you have weighted networks, you should track these powers as well. And then the last rule is that if you have a diagram with more than one blue node, it could happen that you project on one of them and you act with Q on the other. That creates an edge between them. And so this is a way to generate the loop diagram. And so there's 2 ways to do that projection. You can project either here or project there. And so that gives a factor of 2 as well. And so, but these are all the possibilities that this S to I transition allowed. And then you can continue that up to the third order. And these are all the contributing diagrams in that case. And so you see that it will become more complicated, but there's a certain systematics. So if we want to sort of solve this thing at all orders, we have to keep track of all these diagrams, and we should know two things about them. One is, of course, how often do these diagram configurations, how often do they appear in the network that you are interested in, that the system is propagating on. And another thing is that how is the coefficient with which they appear. Because you see, for instance, here, this loop diagram comes with coefficient -3. And that is sort of network independent because it just tells you that this diagram can be constructed in 3 different ways by 3 applications of this matrix Q on the initial conditions. And so the 3 different ways are like the 2 ways that we already saw on the last slide. You take this diagram, you project here and then there, that gave a -2. And the third way is then when you have this chain and you connect, let's say, this blue node to that white node, and that gives another contribution to this diagram. And so because those coefficients sort of don't really depend on the network structure, you can actually obtain recursive relations for them and try to solve those recursive relations. So that's what we'll do in the remainder of the talk. For the case of trees where there are no loops. And so, as I already mentioned, that if you are interested in computing single node expectation values, then it suffices to take the single blue node diagrams. And if there are no loops in the network, then these terms are just not there, topologically, let's say. And the only single blue nodes, the diagrams that remain are just chains. So every time that you have more blue nodes, you always have a branch. So this one branches from patient 0. So this guy on the left is always patient 0. I forgot to mention that. But so this guy branches from patient 0. This guy branches one out later. But the bottom line is that to track the single blue node diagrams, they always have this form of a chain with a blue node at the end. And so that's what we'll do in the tree case. So we construct a tree where we put patient 0 in the middle. We suppose it has k0 neighbors. In this case, k0 is 3. And so at distance 1, there will be 3 nodes, or k0 nodes. And each one of them has degree k1, we'll say. In this case, k1 is also 3. And then at distance 2, at some maximal distance, we'll just stop. In this case, maximal distance is 2. But in principle, it could be a bigger tree. And each one of the further nodes will suppose it has degree k1. All right, so as I mentioned just now, to compute the single node expectation values, we only need to track the chains. So it sort of makes sense because there's only one in a tree, there's only one way for the infection to reach you. If you're, for instance, here, there's only one way to get to patient 0. So there's only the chains we have to worry about. And so we'll just take these diagrams. It's a k-node chain. Patient 0 is on the left, the blue node's on the right, and we'll add them with some coefficients a, k, n. So this n is the order of the expansion, and k is the number of nodes in the chain. So then these rules of the transition rate matrix, they give you a recursion relation that relates, so this coefficient at order n+1 to the coefficient at a lower order, and also to a coefficient at a lower order with one less node in the chain, right? And this recursion relation is not too hard to solve. And the solution is this. And so you see it's sort of composed out of two parts as well. Well, the alternating sign is always there because of this sign. And then this part is sort of the network dependent part that tells you how many nodes there are in the network that are a distance k minus 1 removed from patient 0. And this combinatorial vector tells you sort of the network independent part that tells you how many ways can I create a k-node chain diagram by acting with this transition rate matrix Q n times. And if you work out that combinatorics, it gives you this vector, and well, it's also just a solution of this equation. So you can, if you don't even know how to do the combinatorics, you can just solve this equation and get the same thing. Okay, so if you know the coefficients, it's not so hard to compute the expectation value of the single node. So this is the expectation value of a node that's a distance d away from patient 0, and it goes as this incomplete gamma function that, as you see, is composed out of two parts. So one part is sort of this exponential decay that ultimately, tells you that this term would go to 0 at late times, and so ultimately the node will be infected. But then there's another part where you sort of sum e to the t only up until d minus 1. And so that sort of gives the initial exponential stage of the outbreak. And so if we get the total infected probability, we just get it simply from summing all nodes in the network, and because we know each one of them is just given by this chain result, we just sum all nodes at a distance d up until the maximal distance. And if we take the limit of this maximal distance going to infinity, then you see that indeed you'll get this exponential growth as long as k1 is greater than 2. So what happens if k1 is 2? Then each of these branches that coming out, each of these branches coming out of the patient 0 will be in a line. And so it can only spread one way, the infection, along the line. And so that will give a linear growth. But if these guys have degree greater than 2, then you can infect multiple nodes at each level, and so you get exponential growth. So let's just look at some finite plots. You see, so the maximal depth or maximal distance is growing this way, and so you see that if the graph is quite big, then first you get sort of the exponential phase, and then once you reach everybody, it caps off nicely to total infected probability equal 1. So everybody's infected. This is the S to I. Then I'm almost out of time, but I think I have a time to discuss the rings. So the ring case is nice to illustrate sort of the additional complication of having loops in the network, because it's the most simple graph you can write down that has a loop. It just has one loop, just a big ring. So we take a ring of n nodes. It doesn't matter where we put patient 0 because the thing is sort of translational invariant. So suppose patient 0 is here, then the diagrams that contribute to the expansion, they're going to be chains going around this way, or chains going around the other way. And then you have the extra possibility of having 2 blue nodes in the diagram. So you could have attach a blue node on this side and on that side simultaneously. So those guys we now have to track, because eventually when they complete out the full chain, they're going to join together and form this loop term where the whole chain is connected to the end, and that has a single blue node, and so that contributes to the single node expectation value. So that's something that we want to keep track of as well. And so fortunately, in this SI model, it's quite simple, and you can still solve the set of recursion relations. So now you have 3. You have to find all these coefficients, so the chain coefficients give a very similar relation. Then the 2 blue node coefficients and the loop coefficients actually they look very similar, right? So if I actually fill in k is n+1 here, and then these terms are the same with the minus sign, whereas this sort of the coefficient goes to -2 times itself is also the same. And so actually this implies that there's a relation between 2 blue node diagrams and loop diagrams. And so the contributions that they give to this sum, these coefficients, are equal to minus each other. So the loop diagram gives a contribution minus the 2 blue node diagram that looks like this. And so whichever one so they're the same. So that means that whichever one you find harder to compute or easier to compute, you can compute it and then get the other one. And so the loops are as hard to compute as the correlations between 2 nodes. And this is a statement that is true for this SI model. I'm not sure how it will hold up for more complicated models, but already here, I think it's an interesting observation. In any case, for SIs, it's not hard to solve these recursion relations that I just showed. And the answer will give you this formula for the n node chain. So this is the total infected probability of this n node chain. I don't have terrible many things to say about this formula, except that maybe I can show you what it looks like. So it just grows linearly and then flattens off when you reach the full chain. And of course, because these guys are normalized to 1, if the chain is bigger, the linear growth will be smaller, but they all sort of converge to I equals 1 in the end. Okay, so that's about it, what I wanted to show you. So the discussion, it's possible to gain insight into microscopic dynamics, at least in this very simple example, using the tensor products and formulating this transition rate matrix as a bilocal operator on the tensor product space. I think it's a nice approach. I think there's many more things to do. I've come to understand that the epidemic spreading on network community is not has not looked at this way of approaching the problem. So we could ask many things like, how does this generalize to more complex networks? If we just have more loops or very clustered networks or networks with community structure, how can we sort of use these tricks to say something about that? Of course, the SI model is quite simple. More hard is going to be including recovery, but also more interesting because then you get sort of threshold behavior where there's a phase transition between the infection reaching a large part of the population or it just dying out, and those are the sort of things that epidemiologists are interested in. So it would be interesting to sort of think about how this approach could help understand these microscopic dynamics for other type of models. And one avenue in doing so would be to adapt the use of tensor networks to stochastic systems. And so tensor networks are a mathematical and a numerical technique that are being used in the study of many-body quantum systems. And they're sort of a way to represent these many-body states as a contraction of matrices. So instead of sort of making the mean field approximation and saying everybody's a separable state or separable vectors, you say, okay, every node is a matrix, and to get the many-body state, you have to contract this matrix in a certain way. And that's going to give you a more efficient representation, because these matrices are sort of polynomial in system size, whereas sort of the complete exact states is exponential in system size. So that's the idea of using tensor networks, and this framework is just ideally suited to adapt those techniques. And I'm also interested in trying to think about how this can help and understand questions on stochastic complexity. When is a model simple? When does the model become hard? How much of this exponentially large space are you going to explore by these type of transition rate matrices? Will you only cover, say you start at a deterministic state and then you evolve it in time? Will you only, make a very small, see a very small portion of this many-body state, or are you going to see a large portion of this many-body state? How can you quantify those things? I think those are interesting questions to ask. And with that, I want to open the floor for discussion, and thank you very much for your attention. So there we go.
Thanks a lot. Are there any questions?
Yes, I have some questions. First of all, Wout, thank you very much for this nice presentation. It's, I think it was close to my level of understanding of the techniques that you mentioned. So,
Okay.
So that was very nice. So I'm trying to wrap my head around a few things. So one is, you say this can be used to gain insights, right? So let's stick to the epidemics case. It gains insights. That's what you say. So my question is, does it gain more insights somehow, or can it be that in the future it will gain more insights from doing it in a different way somehow? Do you understand?
That's what I hope. Of course, that's the sales pitch,
Yeah. Good.
But when you say anything about the future, it's uncertain. So I don't know. It's of course true that the example I showed is quite simple. So there, it's all analytically tractable. When you include things like recovery, you're gonna have to track. If you do things this way, you're going to have to track a lot more terms, because at any moment a white node can turn blue by recovery. And so there's going to be a lot more diagrams, a lot more coloring of the diagrams possible. And so that's going to be quite complex. In addition, sort of the recursion relations will become more complex. And so in that respect, I think when doing that maybe you have to really gain insights in that case, you have to maybe resort to other techniques. So
well, I guess my question is more. So that sounds more like pragmatic, like you get many terms, but is there a hope? So you focused on reaching analytical solutions, right?
Yeah.
So is that where, let's say, your sales pitch lies, that it's not necessarily easier to compute in a computer that has to go through for loops, but it's easier to find analytical solutions? Is that the sales pitch?
Yeah, at least this sort of framework would make it possible to find analytic solutions, and I don't know if that's true in another way, actually. So I mean, if you would ask me to solve the SI model on a network, yeah, this is the only way I would know how to do it. So, and in this things that I think it's possible to
but you
do
still
things
have,
like SIR. This would be possible, maybe.
but
SIS, I don't think so.
But you still have the mean field approximations that people have done, right? To solve the model, sort of. You don't consider that a solution? Or?
Yeah, so there's a lot of results in the mean field limits.
Yeah.
Indeed. And and sort of, yeah, and you can see quite clearly that this mean field limits would really sort of the restricting to separable states here. So you those things are sort of contained within this framework. But of course, like the methods that are used to find those solutions are different.
Yeah, I guess the question is like, can you do better than that? I mean, I know that in the paper you have like corrections in 1/n, sort of, to the equation. And can they find the same corrections by pushing their mean field approximations to higher order, or you're getting?
Yeah. So what they do in the mean field, so the mean field approximation that they do is well, first you can say, okay, the nodes that are neighbors are statistically independent. Independent random variables. And that's sort of the mean field approximation that I showed to you. But then what people do to go beyond that approximation to make it more accurate is to say like, okay, maybe the nearest neighbors are not statistically independent, but we'll just keep track of the dynamics of pairs as well, like SI pairs. And then you'll track all the pairs, but in turn, their time evolution will depend on triples. So then you're going to have to track the triples as well. And so that whole set of equations is going to grow until you reach the full system size. And in principle, that whole set of equations you can derive from just the transition rate matrices that I showed in this talk. So the not only the individual based mean field approximations are derivable from these transition rate matrices, but also the pair approximations, the triple approximations, the quadruple, you can go on. But yeah.
But they match. I mean, all I mean is that, you know, you
that match. It's the same. Yeah, it's the same thing. Yeah, it's the same thing. Yeah, it's the same system. Just yeah.
I mean, I have the impression that one important thing here is that the equation that you derive, they allow you to compute average quantity, but also higher order moments, right? Because you compute equations for quantities that are not directly average. Whereas in the mean field approximation, people compute average quantities. So for example, if you want to look at fluctuations, like something that is related to fluctuation of your population. So like if you're interested in correlation function, how correlated are two people in your population, how likely someone in the population who is infected is correlated to another person in the population. For this type of quantity, you cannot use mean field approximation. And
yeah, so
yeah, so I think maybe it would be interesting in your talk if you would come up with some example where you study fluctuations of your system, like coming up with correlation function, for example. I think that would be interesting quantities to compute.
Yeah, exactly. So these are part of the follow-up work that we're working on. And so the idea is that indeed sort of the single blue node diagrams are going to give single node expectation values, and then the multiple blue node diagrams are going to give the correlations. And so then because you know you have to project on multiple nodes to make them give a non-zero contribution in the end. And so that's sort of how to track the correlations between the nodes. Somehow my Zoom is frozen. Can you still hear me?
Yeah.
Yes.
Okay.
Yeah, do you have more questions, Clelia? Otherwise, I'll pass to Janus.
I have a bunch of questions, but so one of them was the fact that I think one of the main improvement here is that you can access to higher order moments quantity. I mean, some higher order moment of interesting quantities in your system that you cannot do with a mean field approximation. And probably this is where, yeah, this is what I was asking right now, that probably you should look at this type of quantities and I don't know, like they are a bunch of quantities that you could look at that you cannot solve with mean field approximation. So maybe we can discuss this later. But the other, I forgot now. The other thing that I was wondering is that is the other improvement of your technique is the fact that you can solve problem with more than 2 states. So if you do the SIR problem, is it easier to do it with your technique than with usual techniques?
So in SIR, in this way, you have not a binary. The states are not the individuals are not binary, so they can take 3 values. So that means that so we still have to track sort of the infected, but then we get blue nodes for the transition from susceptible to infected, and then we'll get another infinitesimal stochastic state that transitions from infected to recovered. So the added complication in doing things like this for SIR is that we now have to color the diagrams with 2 different colors, right? And there will be rules that can sort of tell you how you have to do the coloring. But in principle, yeah, that makes it more complicated, but it doesn't make it impossible, because sort of the trick is that at the end of the day, when if you're interested in single node expectation values, you only need diagrams with 1 colored node. And if you're interested in correlations, you only need diagrams with 2 colored nodes, correlations between 2 nodes, let's say. And so that sort of simplifies it a bit. If the rules, you know, of coloring the nodes in subgraphs are still sort of simple, and in SIR, I think they are still simple. In SIS, even though there's only 1 color, it gets more complicated because you can color in any sort of node in the middle, and then remove the blue nodes at the end of chains. So also things can happen that the blue nodes sort of will loop around these kind of diagrams. The next order, it will go here and there and there.
So you have to enumerate them by hand like that for any cases that you're studying, or enumerate, I mean, or with a computer, but I mean, you have to enumerate them, right?
Yeah, exactly. Yeah. So yeah, you have to find some systematic way of keeping track of all the diagrams. Yeah.
So this reminds me a lot of these Bell's polynomials. I don't know if you know about this. So generally, when we work on branching processes in continuous system, because it's hard to do all the enumeration, if you want to come up with equations for higher order moments, we compute backward equations. So instead of looking at the system and compute forward equation for the problem, we instead look at backward equation, which is some are easier because you have only 1 ancestor. So when you get infected, you're infected by 1 ancestor. Generally, but maybe in the infection problem, it can be more complicated. You might be infected by 2 people, I don't know. But if you assume that you have only 1 ancestor, then generally writing down a backward equation is easier than writing down a forward equation, because you have to come up with these combinatorics when you're going forwards. Yeah. So in continuous system, people use this Feynman-Cat formalism, and we can compute an equation for generating generating functions, and then you derive those generating functions to get the equation for the different moments. So you derive one time if you want the first order moments, 2 times if you want the second order, and so on and so forth. And those derivation, when you do those derivation, you end up with having those Bell polynomials that are those coefficients here that give you all these combinatorics. So maybe that's something that you could try would be, can you derive similar equation in a backward way? Can you do this, your formalism, the backward way?
Yeah, so in a sense, sort of the recursion relation that I discussed, they are in a sense derived in sort of a backward way, because you obtain them by thinking about how the diagram that you're interested in is obtained from diagrams at the previous order.
Mm-hmm.
So going back sort of in time, spreading, so.
But that would be forward, right?
Yeah,
because backward would be, how was it in the previous time given how I am right now? So it would be
exactly
the other way around.
So given that I'm now in this diagram, how could I have gotten here? Yeah. And then that sort of tracks it backward to this one, and then hopefully so that's how those recursion relations are actually obtained. So I think that what you mentioned is very similar. I'm not familiar with those words that you say, but if you could give me some references on that, or we can discuss later.
Yeah, sure.
Yeah.
I sent, yeah. And then the last thing, okay, I can ask question forever, but maybe I'm bothering everyone. But I think I do have a stochastic system where it would be interesting to apply maybe your tensor network formalism, like a multi-agent system. I don't know if you try to apply this on multi-agent systems.
On which system?
On some type of multi-agent system, a system with many agents. Agent competing, for example, here you have many agents that are trying to compete for, let's say, for resources. And each of them has to come up with their own strategy. And I'm thinking that maybe that could be a good place to apply this type of like tensor network formalism. But so yeah, if you haven't thought about it, then we can discuss maybe.
No, I've not thought about that specific example. No, but it could be interesting to think about. Yeah. Thanks.
Janos, you want to ask a question?
Yes. Thanks for the talk. Maybe just a quick question on results. So right now it looks like you have a nice formalism to look at specific instances of graphs. So you're looking at a very regular tree structure or cycle, for example. But typically, I guess, in the real world, you want to be looking at ensembles of graphs, so some graph model, and then to have results. For example, what we heard last week from Clara about a configuration model. So once you've specified a degree sequence, you've got an ensemble of graphs that have some probability of being produced, and you want to have results that's not specific to the instance. So what would be your strategy for extending your results to be able to say something about graph ensembles?
Yeah, that's a good question. I was indeed thinking about extending those this work in that direction. So it requires me to catch up a little bit on the graph theory, that's sort of network theory that people have been using. I was thinking first that there could be some way with generating functions that sort of tell you how to construct the diagrams that I'm saying. But of course, if you have a certain degree distribution of a graph that you're interested in, it doesn't tell you how to put all those nodes together, right? It just tells you that they have a certain degree. It doesn't tell you how much clustering there is, for instance, or how the community structure is. And so the sort of way that we're thinking now about the problem is to really just use the adjacency matrix, because then you can use your configurational model to construct a graph. And then if you're giving an adjacency matrix, you in principle have all the information on how the nodes are all connected. And then, you know, if you follow this procedure in here, you know, the adjacency matrix will tell you about this sort of numbers. How often do these sub diagrams appear in the network that you're interested in? But the other thing, like the coefficients with which each term really appears in this expansion, that one, it doesn't depend really on the network structure. So that's sort of interesting information that you could already compute regardless of whatever graph you have. So, so for instance, you know, there's going to be, each of these diagrams will appear at each order, right? So it's going to sort of give, you can see that here, for instance, the 2-node diagram is linear term. It also appears in the quadratic term. It also appears in the cubic term. And so you can really resum each diagram individually. And so you will know at every sort of network motif, I think people use that phrase, or so every sort of subgraph will correspond to you know, a series expansion in time, which you can resum per subgraph. And so that will just give you the coefficients that you have to add if you have that motif in your network. And then, I mean, then if you have that, I think that the trick is just to take your configurational model, construct a graph with a certain adjacency matrix, and then, you know, figure out what are the subgraphs of that graph, and then sum them with the coefficients that you know, because these coefficients don't depend really on the network structure.
But I mean, then you're still restricting to one instance of a graph. Or would you then say you do it per instance and then?
Yeah, so you want to have results for the ensemble of graphs immediately. Yeah, yeah. So then, yeah, I'm not sure, but perhaps you can do, yeah. Yeah, I still haven't figured out how to do that. So that, I mean, if you know, if you have any good idea, please help out.
Can I just ask for clarification? Are these graphs with a fixed number of vertices, the ensembles of graphs on a fixed number of vertices, or does the number of vertices grow?
So that's related to the sort of configurational model. Yeah, so they will have usually you're given something like a degree distribution. Then you have a fixed number of nodes and a fixed number of edges, and you know the distribution of degrees of the nodes. So
that's what, yeah. So then you have a certain constraint on the degrees, but there are also ensembles that constrain on, for example, triangles or higher order motifs.
Okay, they are constructed in a different way.
Yeah. Yeah.
But should I imagine? I mean, just sorry. I mean, it's not exactly my field, but should I imagine? Would it already be interesting to say fix the number of vertices, but then say, you know, pick edges at random? And I mean, these things could be encoded in a tensor network formalism, for example, somewhat easily, I think. But I'm not sure if that's interesting.
You mean, so you mean then sort of Ehrlich-Renyi?
Yeah, sort of for fixed n kind of, yeah.
That would be the place to start, I think, yeah.
Okay, yeah. Okay.
Yeah, so the idea about the indeed sort of the adding edges at random would give you these Ehrlich-Renyi graphs, and then but a lot of focus is on networks, social networks that have different degrees distribution. So they will have.
Yeah, I think this is more like an indication that I think some models that can well fit into, say, a tensor network description. Like in the end, you can, I mean, for Ehrlich-Renyi is particularly simple. There you just take bipartite interaction to tripartite ones, and you have sort of hidden variables that control whether an edge is there or not. Like people do this in the quantum world as well, like to vary the amount of entanglement between nodes. But you can also add more non-local constraints, or like, you know, other kind of local constraints on like clusters of nodes. way. So maybe that's an interesting direction to go as well.
Yeah, definitely. That's one of the possible directions I want to look into. Indeed. Try to use these tensor networks or some matrix product state ansatz and use these transition rate matrices to involve those things in time and study sort of the properties of the more complicated systems that are probably hard to do analytically. But yeah, for now I've been having fun just trying to figure out how to get these analytic solutions for the simple models, because I think it gives already some interesting sort of insights. Yeah.
So well, maybe one more. I guess this is not really a question, but so right now each node in some sense is an individual, if you want to think in terms of epidemics.
Oh yeah.
But it could be maybe interesting to think of each node as a population with similar properties. Let's say a city or something like that. And, and then I guess your value wouldn't be just 0 or 1, meaning infected or susceptible or whatever. It would have a continuous, meaning a percentage of infected population or something. And mathematically also seems interesting. What if you change these discrete states for a continuous in each node? And I mean,
I think that relates to something in sort of population dynamics and epidemic spreading called meta population models, where they do indeed some these kind of things, or where you have sort of communities that are assumed to be homogeneously mixed, so you can represent them sort of by a complete graph. You know, everybody talks to each other.
Yep.
And then these sort of homogeneously mixed communities are talking to each other through a different network.
Exactly, yeah.
And that could be sort of migration patterns, or it could be just, you know, you have your schools, your schools homogeneously mixed because all the kids they infect each other, but then, you know, the kids go to their own parents, so they infect only. So the parents go to work and they affect a different sort of community. So there's these links between different communities. Yeah, I think that is also quite interesting to think about. Yeah, whether you can, because that sort of relates to something in physics called sort of a renormalization group flow, where you can sort of lump together the microscopic system and replace it with a sort of effective description, like you're saying. Like we say, okay, we'll take the whole homogeneously mixed cluster of you know, kids in your school, and we lump them and we just represent them by one node that has you know, an effective interaction with the other lumped nodes, and then you sort of go to a more coarse-grained level and to apply these sort of techniques. Yeah, that could be interesting to look at too. Yeah. So. Any more questions?
No, doesn't look like so. Let's thank you again.
All right, thanks for joining, everybody.